So here's the deal. So here's going to be your setup. You're going to have a, like for example, on this first set of trials, let me kind of get you through from the beginning. You need a radius of 0.8 meters. So what you want to do is measure from the middle of the stopper to the edge of the tube. Now,
Are you late?
so when you run this through, you would have measured 0.8 meters from here to here. When you're threading this through the tube, a lot of these tubes are going to have like kind of a rougher edge or a smoother edge. Make sure that you put the smoother edge where that string is going to spin around. Otherwise, it's going to get real jerky when you swing that thing around, especially on those plastic tubes. The glass ones, you have to pay attention, but it's not as bad. So you're going to measure out 0.8 meters and then take like a marker and put a mark on the bottom side of that string. So here's the deal. So this is the 0.8 from here to here. But put the mark that you're going to go for on the bottom of the tube. Because what you want to do is that when you start to swing this thing around like this, okay, that way when that purple mark gets to the bottom of the tube, that way this up here is 0.8 meters, okay? So make the mark here, that's going to generate a 0.8 meter. Don't put the mark up there because it's tough to see when you're swinging that over your head. So, get this going around like this, get it going, and then you want to have at least 2 people timing this, okay? And again, you're going to time 10 revolutions. So, like, I don't care how you do it, okay? Some, literally first block, they were laying on the floor, timing it, so they could see exactly when it's counting. Some groups have like the person swinging it counting to 10, some other groups let the individuals count to 10. I don't care, okay? Whatever works for your group. But again, here's the main thing. Those times have to be pretty close together because if they're not, somebody didn't count to 10, okay? So that's the most vital thing. So the whole key to this lab is that centripetal force is going to equal mv squared over r. So on trials 1 through 4, we're going to make that centripetal force bigger and bigger and bigger. So the key assumption that we're going to make is that whatever the weight is of this mass hanging down is what's creating the centripetal force, okay? So on this first trial, you're going to have a 0.1 kilogram mass hanging from the end. So on that column, here's your mass, 0.1 kilograms. About halfway over, you have a column that says centripetal force. That's the weight of what's ever hanging down. So if you've got a 0.1 kilogram mass hanging down, that's going to weigh 0.98 newtons. So we're going to assume that that gravitational force pulling down is what's creating that centripetal force. So your centripetal force column is the weight of what's ever hanging down. Yes, ma'am?
When you up the hanging mass, doesn't the radius change?
No. We keep the radius constant. Okay? We'll change the radius eventually.
Oh.
But here's the whole thing. On trials 1 through 4, we're going to increase the centripetal force. The radius is still going to be from the edge out to that stopper. Okay? That's not going to change. And then we're not going to change the mass of the stopper either, okay? So those are going to stay the same. So over on page 2, okay, if you flip that over, on each of these sets of trials, we're going to keep 2 variables constant, and we're going to change the other 2. So on trials 1 through 4, we're going to change the centripetal force and the velocity. We're going to keep constant the mass and the radius, okay? So if you wanted to, you could take that mass, and you don't have to do this, but here's the mathematical model. You can take the mass of the stopper, divide that by the radius, 0.8, and that would give you some number. okay? So basically, that's just going to be centripetal force equals kV squared. K is just a constant. So this is why when you graph this, and you're going to end up with 3 different graphs. So you can take one sheet of graph paper and divide it up into like 3, or you can put one on each sheet of paper if you really want to kill trees. That's up to you. But you're going to graph centripetal force here, velocity here, and this should produce like a parabolic curve, okay? Because of the fact that it's y equals kx squared. That's the short version, okay? So that produces a parabolic curve. When you plot that data, and let's say you have 3 that are pretty much on that line, and you have one that's completely off of it, either above or below, redo that trial, okay? You have done something horribly wrong, because this should produce a nice parabolic curve. Somebody didn't count to 10. Okay, so on question number 4 on page 2, I asked you to explain the results of the graph. When question number 4, and this is going to be the same on 4, 8, and 12. When you answer questions 4, 8, and 12, you want to mention all 4 variables, okay? So you want to mention centripetal force, mass, velocity, and radius. So here's how you can answer question number 4, okay? You can just say something like this. As centripetal force increases, because that's what's happening, because you're producing more and more weight that's hanging down below. So as the centripetal force increases, velocity has to increase because mass of the stopper and radius are constant values. Okay? So when you give this explanation on 4, 8, and 12, you want to mention all 4 variables, right? Now the other option, the other thing you could kind of reverse it, and you could say, well, since the mass of the stopper and radius are constants, as the centripetal force increases, velocity has to increase. Okay? I don't care how you do it. Just make sure on 4, 8, and 12 that you have mentioned all 4 variables. Explain how 2 of them are constant and how 2 of them are changed. Let me give you a hint. Your velocity is always a changing variable. Okay? Velocity is always changing. Now, on 5 through 8, you want to change the radius. Now, when I say change the radius, I mean change the radius. I'd start at, don't go anything smaller than 0.5, okay? But I'd go at least maybe 10 or 15 centimeters in between, so you could go like 0.5, 0.65, 0.8, 0.95, something like that, okay? But at least have 10 to 15 centimeters of distance. Now, this is going to create a bit of a challenge on your marks. So this is why when you get to that one, so if you have like, I've got like different colored markers in the room. So what you can do is make your different radii on here like a different color. So like this one was purple. You could do another one like in black, another one in red, something like that, okay? The other thing is, if in doubt, like if you've got a whole bunch of marks on here and you've completely lost track of what is what, I got a whole bunch of string. The string is cheap. Throw away the string and just start over with a new piece of string, okay? So don't be afraid. It's like, oh, the string is precious, okay? And it is, but there's also a point where, okay, we have no idea which marks we're looking at now. Let's just start over with a new piece of string. So when you look at this one, on 5 through 8, centripetal force equals mv squared over r. So on 5 through 8, now you're going to keep the centripetal force the same. So you could pick any of those masses. You could pick 0.1, 0.2, 0.3, 0.4. I'd recommend that you pick either 0.2 or 0.3, okay? 4 is tough to do because you have to spin it really, really fast because you're generating so much centripetal force. 0.1 gets a little sketchy because it's almost like sometimes you have to go really, really slow. So 0.2 or 0.3 are kind of in that Goldilocks zone. So on trials 5 through 8, I don't care which one you do. Either pick 0.2 or 0.3, and you're going to use that for all 4. Now, here's what you want to look at. So again, on this one, your centripetal force is going to remain constant. The mass of the stopper is going to remain constant. So these 2 variables aren't going to change. So, as the radius gets bigger, as you divide by a bigger and bigger radius, Zoe, what's going to happen to that velocity? I want the same value over here, okay? But I'm going to make my radius bigger and bigger and bigger. So what's that going to do to my velocity? Will it increase or decrease?
Your radius is bigger, you said?
Yes.
Decrease.
What'd you say?
Decrease.
You want it to increase. Here's the reason why. You're dividing by a bigger and bigger number here, right? And you always want this to be the same, so that also has to increase. But it won't increase in a 1-to-1 ratio because that velocity is squared, okay? So what you should see on trials 5 through 8 is that as your radius gets bigger, your velocity also gets bigger, but just not in a 1-to-1 ratio, okay? Now, on 9 through 12, you're going to keep the same centripetal force. And you can keep the same value that you used on 5 through 8. I don't care, just keep the same one. You're going to keep the same radius. I don't care which radius that you pick. Pick radius. Just make sure that it's the same. But now you're going to begin to alter the mass of the stopper. So I've got different size stoppers. You can also tie a couple of stoppers together if you really want kind of a bigger change. So on this one, as the same centripetal force, same radius. So as the mass gets bigger, what has to happen to my velocity? It's got to get smaller. Okay, so this is the only one that's like an inverse relationship. As the mass, so what you should see is the mass of the stopper gets bigger, the velocity should get smaller. Okay, with all that said. So again, I cannot emphasize this enough. When you answer questions 4, 8, and 12, you make sure that you have mentioned all 4 variables. Okay, now when you get to question number 13, you want to look at trials 4, 8, and 12, and you want to see if your velocity actually matches up with the idea that the centripetal force is created by the hanging mass. So here's what you're going to do on trial number 4. You're going to calculate experimental error, but the first thing that you need to do is calculate centripetal force using mv squared over r. So what you're going to do, you're going to go to trial 4. You're going to find the mass of the stopper. This is not the mass of what's hanging down below. This is the mass of the stopper. You have a column there that says velocity. Oh, you're going to know what that velocity of the stopper is. And you're going to know that radius is 0.800 meters. So you're going to calculate centripetal force using mv squared over r. You're going to go to the trial, and you're only going to do this on trials 4, 8, and 12. I don't want all 12 of these, just 3 of them. So you're going to go to trial 4, calculate centripetal force this way. Then you're going to compare it to what it should be, which is 3.92 newtons. Because if you take 0.4 kilograms times 9.8 meters per second squared, you get 3.92 newtons. So on trial number 4, you're going to take 3.92 newtons minus what you get out of this, mv squared over r. Divide that by 3.92 newtons times 100. Okay, so it's going to be your theoretical of 3.92 minus your experimental divided by your theoretical times 100. And then you're going to do the same thing with trial 8 and the same thing with trial 12. So again, the theoretical is going to be the weight of what's hanging down. Okay, and that's going to change depending on which group, what you guys choose to use for those. But this part's going to, this part is going to be the same for everybody. But you're still going to use mv squared over r to get your experimental. You're going to use the weight of what's hanging down to get your theoretical. Okay. So what's the next one? 14? Where you have velocity and, no, you have centripetal acceleration and g's. Okay. So again, you're just going to go to trials 4, 8, and 12, and you're going to calculate that centripetal acceleration using v squared over r. Okay? Go to your column, it says velocity, find the radius v squared over r. Yes?
You should just say an answer from the other question.
No, because that up there, you're finding centripetal force. This is just finding centripetal acceleration.
Oh, right.
So, let's say that you do that, and let's say that you get 19.6 meters per second squared. Okay, just make up a number. So, G's are a measure of what that value is compared to your normal gravitational acceleration. So to get your G's, you take that centripetal acceleration and you divide it by 9.8. So in this case, if you take 19.6 and divide it by 9.8, you're going to get 2.0. So what that means is if you were that rubber stopper, look.
You dropped it.
Oh, thanks. If you were that rubber stopper on the end of the string, okay, that means you would feel twice as heavy as you do right now. So right now, you all are used to lifting your arms under 1 G, okay? If you're 2 Gs, your arms would feel twice as heavy. If you're 6 Gs, your arms would feel 6 times as heavy, okay? Typically, people pass out around 2 to 3 Gs, okay? You get upwards in the upper teens of Gs, you begin to like break bones and blood vessels. It's kind of bad. Okay, so again, you're only going to do that on trials 4, 8, and 12, okay? Now, your next question, you want to calculate the centripetal force needed to keep our rock in orbit around our star, okay? And obviously this is going to be a really big number, okay, because we have a pretty good sized rock, and that's cool. So what you want to do on that one, you're going to use centripetal force equals mass 4 pi squared r over t squared. So how long does it take for our rock to go around our star? 365 days. But what are you going to do have to do with those 365 days? Convert it into seconds, because I want a force which is kilograms meters per second squared. So make sure that mass is in kilograms, make sure that radius is in meters, and make sure that period is in seconds. Now, when you do this, when you convert that year into seconds, don't round that number, okay? 1 year is exactly this number of seconds. Some of you are rounding way too early and it's annoying. Stop, okay? When you do a subcalculation, you want to keep more digits than what you need and then round when you get to the end, okay? So, when in doubt on your, like these conversions or a subcalculation, keep more digits than what you need and then round when you get to the end, okay? Now, when you get to the next question, you want to figure the centripetal force needed to keep someone standing on the equator as they go around on a spinning rock, okay? So, it was odd yesterday, someone posted a story on my Facebook timeline. It was like a problem from the physics book. And it said, it involved a penguin, and it said, okay, we're going to model the penguin as like a round cylinder. And it was just like, how weird is that? Because, you know, yesterday we talked about Polly the penguin, and it was like, they posted that story. It's like, I said, ironically, we used penguins in class yesterday. So, here's the deal. So here's Polly the penguin, go around on the spinning rock. Because we're spinning like this, right, we're undergoing centripetal acceleration because we're traveling in a circle, okay? So it's going to require a certain amount of force to make that happen. So again, on that question, on the centripetal force needed to keep a 70 kilogram person on the Earth, you're going to use this equation again. This is going to be the mass of the person. This is going to be the radius of the Earth. How far are you out? How far are you from the center of the Earth? This is going to be t. Now, if you're talking about our spinning rock on its axis, what are you going to use for t here? Yeah, 24 hours, right? So on that one, you're going to start with 24 hours and change that into seconds. So for the Earth going around our star, you're going to use 365 days. For the Earth spinning on its axis, you're going to use 24 hours. But pay attention to the units, that this is in kilograms, meters, and second square, okay? Now, on the last question on the lab, you've got this rubber stopper, okay? You want to draw all the forces to scale, listen to me, Mason, to scale with a ruler, okay? This isn't a freehand sketch,
Why not?
because I said so. So, you're going to have a rubber stopper moving around in a circle. You're going to choose the scale, and this is going to be only for trial 1, okay? You're not going to do this for all 12 of them, just for trial 1. So you're going to figure out, okay, hey, what forces are acting on this rubber stopper? Set up a scale. Some of these numbers are probably going to be pretty small, so you might let like 2 centimeters equal a newton. I don't care what the scale is, just make sure that I see what that scale is. Okay, so let me hand out this blue sheet. Don't flip out on this one yet. This is just so you have it.
Let me know what you get.
It's gonna be one thing.
I said I just need one. How do you retire?
Don't ask me.
Mr. Bergkamp,
Yes.
when is our test gonna be for this?
Oh, we've still got all of planetary motion to go.
Oh, okay.
There's the test is where you
Was
start.
that
Sounds
the test for
good.
projectile?
Huh?
Is that the test for projectile, or is it gonna be on the same test?
Projectiles included in
What do you mean?
I was asking if the projectile's gonna be on the same test.
No, that's,
It's different to the quiz that we just took. That stuff isn't gonna be.
yeah,
on
it's
that
just
one.
gonna be centrifugal motion and gravitational fields. Okay, so don't flip out. Let me explain what's gonna happen. So kind of like, it's a weird deal the way this played out with that quiz and everything. So here's the drill. So the lab, basically today is gonna spend collecting the data from the lab, okay? That is probably gonna take about the entire time to get all of the data collected. So tomorrow is basically gonna be a work day. So this blue assignment and the lab are both due on Thursday, okay? So the lab and this assignment are both due on Thursday. Tomorrow at the beginning of the class, I'll spend a lot of time going over some of these questions on this blue sheet. But, and again, do not answer these on this, okay? So, I'm basically done. So today, lab, tomorrow, finish up the lab and work on the blue sheet, okay? Ready? Frank, here we go.